Hello again. So I couldn't do a set of videos on thunderstorms and tornadoes without actually talking about thunder. So let's talk about thunder and what causes thunder and what causes lightning. And one thing's for sure, you can't have thunder without lightning, but you can see lightning and not hear thunder. So we're going to talk about that a bit more too. It's all about physics, so let's get into it. Lightning is the discharge of energy in a cloud or between clouds or between a cloud and the ground. A discharge of energy. It occurs in mature storms, not developing storms. And thunder is the sound wave from the discharge. So it is actually an explosion in the air that you're hearing. So how do we electrify a cloud? We know that the top of the cloud is colder than the bottom of the cloud. And we know that the top of the cloud is generally positive. And for the most part, the bottom of the cloud is generally negative. There are some cases where, especially in the downdraft, the cloud is colder, and those parts of the bottom of the cloud by the downdraft will be relatively positive. But overall, the bottom of the cloud is generally negative, and the top of the cloud is generally positive, and our ground and our trees and so forth are generally positive. So you can see how this is setting up for opposites attract. And you can understand why you should avoid trees and staying dry under trees during a thunderstorm. Just get wet, because the trees are at an elevation and they're positive. They're going to attract the lightning bolts. So while they may keep you dry, you might also be fried there. So avoid the trees. And hold on a second. Let's go into the theories of how a cloud becomes electrified. There's a lot on this slide. We're going to take it apart bit by bit. And so you know that, especially during the summer thunderstorm season, that you can see hail. You know that the top of the cloud is colder and that the top of the cloud has ice crystals. When ice crystals bump into rain droplets, the rain droplets are going to conduct heat right to the ice crystal, and the ice crystal is going to freeze the raindrop to it, and in freezing, remember, we are releasing energy. Remember the hand warmer. In freezing, we are releasing energy. So that overall, the theory is that the hailstone or the ice crystal to be, well, let's call it the hailstone, that the hailstone stays warmer than the ice crystal and the raindrop that freezes to it, because you've got a lot of latent energy that is in the vicinity of this hailstone as the freezing is taking place. So now you have a warmer hailstone and a colder ice crystal. You have a system that is not in equilibrium. And you know that the energy needs to transfer from the warmer environment to the colder environment. In this case, the theory is that this transfer takes place for positive ions moving energy from the hailstone to the ice crystal or the raindrop. When I'm moving positive ions away from the hailstone, I am making the hailstone less positive. In making the hailstone less positive, I actually make it more negative. And in making it more negative, I could have a hailstone that has some mass to it that is dropping down to the bottom of the cloud and creating a negative environment, versus the raindrop with the little itty bitty ice crystal, which is now positive because it has those positive ions, and has very little mass, so it can be rotated up to the top of the cloud and produce positive electrical charge at the top of the cloud. That's one theory about this. Another theory that's related to it is saying that all of these collisions on the way down from this hailstone, of course they will freeze the ice crystals and raindrops, but as they freeze those ice crystals and raindrops, instead of the ions moving from the hailstone to the raindrops and ice crystals, instead of that happening, those ice crystals that have collected at the edge of the hailstone just splinter away. And as they splinter away, those ice crystals are more positive. So in either way, the ice crystals are going to be more positive and the hailstones are going to be more negative. It's just a matter of how they got more positive and more negative. That is in the theories. You see how this sets up for a negative charge attracted to a positive charge for cloud to ground lightning. That makes sense. You could see that different cells in the multi-cell or the supercell thunderstorm could have different levels of potential because some tops of cells are near the negative areas of other cells. So you could see that jumping back and forth. There are generally four patterns to the formation of lightning, and that is for cloud to ground lightning. It starts with a stepped leader, then a return stroke, and a dart leader. Let's go into it and show you some pictures. A stepped leader is feeling your way through the atmosphere when you're a lightning bolt. There's a lot of resistance in the atmosphere toward a lightning bolt coming through. A stepped leader plows out the way so that the bolt can come through. A stepped leader, then cloud to ground lightning, and then a return stroke. You often don't ever see the stepped leader. You see the return stroke. Watch it closely sometimes. And that is a powerful stroke back to the negative section of the cloud and bringing the positive ions back with it. So you're just setting yourself up for some more lightning and some more potential. There are different forms of lightning. The forms of lightning seem to align themselves with different areas of the world and subject of a lot of research. You may not have seen these kinds of lightning because you're not in that section of the world, but forked lightning we certainly see. Ribbon lightning I have never seen. Beaded lightning I have never seen. Perhaps you have. Ball lightning is not uncommon, but hard to find. And we see sheet lightning around here, which can be between the different cells that are at different levels of potential. You can understand different tops, different bottoms. And then heat lightning on the surface. It's all about energy, right? When you see something like, you might have heard of a movie in the 80s, St. Elmo's Fire. It's a great college movie. St. Elmo's Fire is actually after a first type of lightning rod before Benjamin Franklin developed the lightning rod. And so ships' masts used to send off warnings about an impending strike. Now remember, this is in the 1700s. The ships are made of wood. They cannot catch fire. It would be devastating in the middle of the ocean. So the ship's watch would really notice if the mast was glowing with the positive charges that happen right before a strike. You see it moving up in there. And they had all fire brigades to try to cool the masts so that they wouldn't start a fire. Consequently, this is a famous photograph in your book for a set of brothers that were taking pictures because this was exciting on their hike. Moments after this, the lightning bolt struck both of them unconscious, killed a person near them, and injured several others. So you might think this is very exciting. If you notice that, if you hear rings, you'll actually hear them vibrate. If your hair stands on end on a hike and you see cumulus clouds above you, don't get under a tree. Get out and spread yourself out on the ground as best you can. And that might help you, but definitely get down on the ground and don't be standing up. In regards to thunder, there's always lightning before thunder, and it's generally the thunder is generally traveling slower with the sound waves than the lightning, of course, and so it is 5 seconds to a mile, which is why you say 1 Mississippi, 2 Mississippi, 3 Mississippi, because you're trying to replicate the 5 seconds so you can figure out how many miles away the storm may be. Now, there are different types of thunder. You can hear a clap of thunder. You can hear rumbling thunder. You might see the lightning and hear no thunder at all. So let's talk about those 3 different types. I can show you on here rumbling thunder. So if you have thunder that is just from let me start this. So if you have rumbling thunder that goes on and on and on, it's coming at you from many different places, generally coming at you from the cloud and from the ground. And then you hear it at different times and it seems to rumble on and on and on, or it could echo along a valley. In addition, you might hear a clap of thunder that is from one place, generally from the cloud. And it's generally right on top of you. And you may not hear thunder at all, because if you are standing away from the storm, the thunder sound wave can hit the ground and bounce off above you. So you may not hear the thunder at all. So 3 different types of thunder for thunderstorms. I hope that gives you something to think about. I'll see you on the other side. Get to tornadoes.